Dr. Ranjani Parthasarathy is a professor in the Department of Information Science and Technology, Anna University. Her area of specialization is computer architecture and networks. One of her special interests is Indian language technology systems. She is actively involved in research in all the areas and has over 50 publications to her credit. She has about 25 years of experience covering both industry and academics.
Welcome to the UGC lecture series in computer science. This is a series of lectures in computer architecture. We've been looking at arithmetic unit, we looked at adders, subtractors and multipliers. So we looked at some parallel multipliers and sequential multipliers. What we will be looking at today is a little bit more on multiplication. We will look at one fast multiplication technique and then take a look at division. So let's look at this fast multiplication technique, which is basically based on what is called as a carry save addition technique. So let's look at the idea that is used in this. So look at our normal multiplication process, right? So I have say M0, M1, M2, M3 which are my multiplicand bits, and Q0, Q1, Q2, Q3 which are my multiplier bits. So typically what is it that I have? I have M0, Q0, the AND of the different terms, right? Assume that you are doing an AND of all the multiplier bits with all the multiplicand bits, which gives me these M0, Q0, M1, Q0, M2, Q0, M3, Q0. Similarly, M0, Q1, M1, Q1, M2, Q1, M3, Q1 and so on, right? All the ANDs, I have got all the ANDs in position. Now it's a question of how I add up all these ANDed numbers correctly, so that using these full adders, so that I am able to produce this complete product of P0 to P7. Okay, this is the normal multiplication process that we have. What we are trying to do basically is, since there are so many addition operations that need to be done, we are trying to see if you can speed up this addition process. Okay, so look at what is normally done. Say, let's say I have got this M0 Q0, that will be my first product P0. Now M1 Q0 and M0 Q1 will be added with of course the carry input as 0, and that gives me my P1. Now the carry from this has to be added to M2 Q1 and M1 Q1, I'm sorry, M2 Q0 and M1 Q1, right? That output will give me some number. So to that I have to add M0 Q2, right, and that will give me my P2. Now this will produce a carry. This carry has to be added along with this number. So what we have here is, now the carry has to go from here to the next bit, from here to the next bit and here to the next bit. So this carry propagation time, okay, that adds to the time taken for the addition along a row, and the sum that is produced by each of these terms here has to be added for getting these partial products, right. So there is a delay that takes place because this addition has to be done over here also. Now obviously before this addition is done, you can't proceed with this addition because this output has to come here, okay. So the question is, can we speed up this kind of a process? Now as it turns out, if you slightly rearrange the additions, okay, the kind of additions that actually get done, we find that you can come up with a faster addition. So let's look at how we rearrange this. So look at this picture here. So what I am doing here is, now instead of passing the carries along the rows, what I do is a carry which is generated here, I know I can add it to the next, this carry which is generated here is added along with the next set of partial products that is here. So let me just go back here, tell you what we are doing here. So what we do here is, now you see that for this partial product P2 to be generated, what is actually getting added? M2 Q0, M1 Q1, M0 Q2, right? All these three are added along with the carry which is coming from here, right? So we said these two along with this carry, and then we added this sum along with this M0 Q2 to produce our P2 here. Now what we are saying is, let's just rearrange this. How do we rearrange this? M2 Q0, M1 Q1, instead of adding this carry here, I will add M0 Q2 over here. Now remember, all the M2 Q0, M1 Q1, M0 Q2 are all generated at the same time for me. So I have all these three AND terms, these three I add over here, and this will produce a sum. Along with the sum, I will add the carry which comes from this previous step. So put this here and put this carry over here. This is what we do. If you change it like that, what is the advantage that you will get? That all these additions, this first stage additions can all take place together. Once that addition is over, without waiting for this carry propagation, you can now do the next step addition. So, this carry propagation time that we have here, we will save, okay. And it is called as a carry save addition because we generate all the carries, save them up and add them in the next step, okay. So, this is what we do. So, look at this picture here. So, just take the same example that I talked about, M2Q0, M1Q1, M0Q2. These three are added over here and this sum which comes from here and the carry, remember, which comes from the previous stage, that gets added here. These two are added to form my partial product P2. Same process is followed at each step. So, look at what I will do here. In this step similarly, I have M3Q0, M2Q1, M1Q2 being added, okay, and that will produce a sum to which I will add M0Q3 and also this output of this carry output which comes from the previous full adder. So, look at this. So, this carry propagation we have cut and instead we are sending that carry to the next stage. By doing this, what we are actually doing is this entire stage, right, all these 4 additions can just take place in parallel without waiting for the previous full adder to get full adder's output to become available, okay. So, this entire step can be done in parallel, this can be done in parallel, this can be done in parallel and so on, and then we keep adding these terms correctly. Once you understand this idea, we can see how this can be extended now for any number of bits in the multiplier and the multiplicand. So, let us just take a quick summary of what we have here. So, let us take this example that will become easier to understand. So, I have these multiplicand 101, 101, 45 and the multiplier Q which is all ones, let us say, okay, 63. Now, what we do therefore is, first of all I am generating all the terms are being generated. How do I generate all these terms? Now, these are all my M0, Mi into Qi basically. This is M0 Q0. This term will be M1 into Q0. This is M2 into Q0. This is M3 into Q0. This is M4 into Q0. Okay. This term similarly will be, this now will be M0 into Q1. Okay. This is M1 into Q1. This is M2 into Q2 and so on. This is multiplication with Q0. This is multiplication with Q1. This is Q2, Q3, Q4, Q5. So, all the AND terms I have got over here. Now, the question is, how do I add them up correctly? Okay. So, what we do is, look at this as my row A, let me call this as row B, let me call this as row C. So, what I basically do is, if I look at this position here, right, I can add these 3, A, B and C together, and similarly I can add this D, E, F together. So, this and this can be added, remember, in parallel, and then the output of this and this output of this can now be added together to produce the answer 0, and that will produce a carry which I will add to the next stage. You can't totally avoid the carry propagation, there will be some carry that needs to be carried over to the next stage, that can't be avoided, but we are trying to reduce the amount of this carry propagation here, okay. So, let us take this forward and see how the complete addition can get done fast using this technique. So, the same number I am taking here, 101, 101 with all ones here, okay. So, let us take this first 3 A, B, C, the 3 different things that I have here. Okay, this first partial product, let me call that as A, 101101. Second partial product 10110, let me call this as B. Third partial product, let us say, is C. Okay. So, what we do here therefore is, now I can add these 3 partial products can now be added in parallel. Okay. So, we have these 3 partial products, right, A, B and C that we have. Now, these are being added. When I add these 3, remember with the full adder I can add 3 numbers, right. So, I will take the first 3 things and add each of these using set of full adders. So, I have 1, 2, 3, 4, 5, 6, 7, 8 full adders, let us say, okay. The 8 full adders now add these numbers and they will produce a set of sum bits and a set of carry bits. So, let me call the set of sum bits as S1 and call this set of carry bits as C1, okay, keep them as it is. Now, remember I have only multiplied the first 3 bits. Similarly, I would have multiplied with the next 3 bits, let me call the D, E, F, okay, these are my 3 other partial products. Now, these 3 partial products similarly now can be added using a set of full adders to produce another set of sum bits S2 and another set of sum carry bits C2, okay. So, look at what we do now, okay. Now, I have got the first 3 numbers have been added, that's produced me, that's given me S1 and C1. Next set of 3 numbers added given me S2 and C2. Now, I have to correctly add S1, C1, S2 and C2 to get the final answer. So, how do I do that addition? Remember what I have to add, I will add the S1, the C1 and the S2, okay. These 3 will be added, S1, C1 and S2. These 3 now will be taken, added using a set of full adders. Now, remember when I add this will again produce one set of sum and a set of carry bits. So, it will give me a set of S3 and it will give me carry bits C3. So now this S3 C3 has to be added, remember my C2 is still to be added. So I will add this S3 C3 and the C2 together, okay. When these get added, this will produce an S4 and a C4, okay. So now when I added this, I got S3 C3, okay. So these S3 C3 and C2 when added gives me S4 and C4. Now this S4 and C4 when finally added will give me the final product, okay. So what have we done by doing this carry save addition? At every stage you generate the sums and the carries separately, keep the carries separately, keep the sums separately, and then add up the correct sums and the correct carries to come to the next step, okay. So by doing this repeatedly, that is grouping all your partial products into groups of 3, adding them using full adders, and then those sums and carries are taken together and added. So you just have to figure out all the numbers have to be finally added, all the sums and carries produced have all to be finally added to give you your final product. So that is all that you need to remember. So you can now do this for whatever be the number of bits, it can be a 6-bit number, 8-bit number, 9-bit number, 12-bit number, whatever. Only thing that many number of additions will have to be carried out, okay. But it will be faster than our sequential addition that we do. So this is why it is called as a fast adder. Summarize on this carry save addition technique that we have. So what are we doing here? So what we do is we group what are called as the summands in 3s and perform the carry save addition on each of these groups in parallel to generate a set of S and C vectors in one full adder delay. Why do I say one full adder delay? Because remember that is all it will take, one full adder, right. This one full adder delay is all that it requires to add this entire thing and produce the sum and carry, okay. So in one full adder delay I will get a set of S and C. Now you will group all the S and C vectors into 3s and keep on performing carry save addition on them, generating another further set of S and C vectors in one more full adder delay. So you will have 2 full adder delays and you would have generated another set of S and C vectors. Now you will continue this process until there are only 2 vectors remaining, and then these 2 vectors can now be added using either ripple carry adder or carry look ahead adder to produce the desired product, okay. This is what we saw over here, okay. So we saw that there are 6 summands, so we divided into groups of 3, so you got one S1 C1. Now this entire thing took only one full adder delay, so this entire took only one full adder delay, so 2 full adder delays here, and this whole thing took another full adder delay, this is one more full adder delay, this you can look at it as a final adder. So 4 full adder delays plus one final addition using carry look ahead or whatever, that gives me my product. So you can see that the total time taken will be much less compared to our sequential addition. Trick to remember here is that we are saving up the carries for the next step and adding them, okay. So this is very useful technique that is used for fast multiplication. So with this we have looked at multiplication techniques. We will take a break now and come back and look at some division techniques. Welcome back after the break. So we have been just looking at some arithmetic circuits, we looked at multiplication and we looked at one fast multiplication technique. With this we have looked at actually 3 different multiplication techniques. We have looked at a parallel multiplier, we have looked at a sequential multiplication, and we also looked at this fast multiplication. Now it is time to take a look at how division is performed. So coming to division, there are essentially 2 techniques that we will look at. One is called as the restoring division method and the other is the non-restoring division method. Now the restoring division method is very similar to the manual division that we do. So let us first take a look at what we do in manual division and see how that is carried out using some circuitry for doing our to come up with our division circuit. So let us look at this manual division. Remember let us say this is the decimal numbers 274 divided by 13. So remember what we do, we look at 27, we see whether 13 will go in that, okay, it will go 2 times, so you multiply it, you get 26, you will subtract, get your partial remainder, and then it is called as a partial dividend, you take the next bit. Now this partial dividend you divide with this divisor 13, okay, remember this is called the dividend, this is called the divisor, this is the quotient and that is a remainder, okay, just reminding of these terms that we normally use. So 14 minus 13 will give you 1. So it gives you 21 is the quotient, 1 is the remainder. Same thing carried out using binary number, okay, 1101 in binary representation. This is 274 in binary representation, right. So when you do this process, what do? Again we do the same thing, 1000, we know that 1101 will not go in that, so we take the next bit also. Now 1101 will be subtracted from that, you get a partial thing, you bring in the next bit, do the subtraction and so on, right. So, this is what we do. So, now this is what we are going to try to do using a circuitry for doing division. So, let us look at this longhand division steps so that we will be able to come up with a circuit which will be able to do this division. So, what are we doing? You position the divisor appropriately with respect to the dividend and perform a subtraction, right. Remember that is what we do. We position the divisor correctly and then perform the subtraction. Okay. So, and what do we do? If the remainder is 0 or positive, right, a quotient bit of 1 is determined, the remainder is extended by another bit of the dividend, the divisor is repositioned and another subtraction is performed, right. This is our normal division process. If the remainder is 0 or positive, a quotient bit of 1 is determined. Let us say for instance we just did a subtraction here, okay, and we found that the what we got will be a negative number, that is this does not go within this. When it does not go, what is the meaning of that? That means if I do a subtraction, I get a negative number. So, if I get a negative number, it means that I will put a 0 as my quotient bit, right. So, this is what we are saying here. So, if the remainder is 0 or positive, okay, then I know that the quotient bit will be 1. The remainder is extended by another bit of the dividend, you are bringing in one bit from above, and then the divisor is repositioned and another subtraction is performed, okay, this is what we do. If the remainder is negative, a quotient bit of 0 is determined, the dividend is restored by adding back the divisor and the divisor is repositioned for another subtraction. Now, this is an implicit step when we normally do our manual division. When we do manual division, what do? We just look at it and we see whether this divisor will go within this dividend or not. What do we mean by saying it goes within the dividend? Whether it is less than this number or not. If it is less than the number, when I do a subtraction, I know that I will get a positive number. If it is greater than this number, if I do a subtraction, what will I get? I will actually get a negative number. And what is the actual step that I do? I can say if it is negative, then I will just add back this value so that I get back the original number. Okay. If you look at it from that point of view, you can see how the whole thing can be automated, which is what we are saying here. That is, we say if the remainder is negative, a quotient bit of 0 is the value that will be chosen, that is determined, and the dividend is restored by adding back the divisor. So, we add the divisor back so that you get back the original number, and then the divisor is repositioned for another subtraction. Okay, you will bring one more bit from the dividend and you will do the subtraction. Okay. So, this is what we are now going to do using a circuitry. So, what is this? What is the essential thing we are looking at? We will do a subtraction, see whether the answer is positive or negative. If the answer is positive, that means my quotient bit is 1. I can proceed, I can shift, bring one more bit of the dividend and do the subtraction. If it is negative, then I know that I can't proceed, right. So, what I will do is I will restore the value back. How do I restore the value back? I will add back the divisor. I subtracted something, I got a negative number. So, if I add back the number to the divisor to that, I will get back my original number. So, I will just add it back, which is what I call as restoring the divisor. So, you will restoring the dividend by adding back the divisor. So, you restore the dividend. So, this is why this is called as a restoring division method. Okay. That is this explicitly restoring the value back, that is what we are going to look at. So, if you look at the circuitry for this is the arrangement that we have. Now, if you look at this circuit arrangement, you can see that this is very, very similar to the sequential multiplication circuit that we have already looked at. Okay, you can see, yes, this is a very similar circuit arrangement that we do, but only thing is in the case of multiplication, okay, we would have done a shift right operation. Instead, here we do a shift left operation. So, let me also just explain that. So, look at what we have here. Now, if you look at this division process, you can see that we keep shifting the dividend keeps getting shifted right, okay, and you are positioning the divisor appropriately there and doing the subtraction. Again, the same thing can be looked at as divisor remaining in the same position, but the dividend being shifted left in order to do the subtraction. Okay, if I keep this constant, if I do not shift this fellow right, keep this constant, it means this fellow will get shifted left. Okay, if this position is remaining constant, okay, this fellow is getting shifted left, shifted left, shifted left and so on. Okay. So, that is the idea that we use for doing the binary division in using the sequential division technique. What we have therefore is two registers, this register A and this register Q, right. This will contain the dividend. Okay, this A and Q will have the dividend. The divisor is in this register here M. Okay, so the AQ has the dividend, M will have the divisor initially. So, what do I do now? The process goes like this. What I will have to do is, you will do a subtraction, right, of this divisor from this dividend. when we do this subtraction, the answer that you get back here could be a positive number or a negative number. Depending on whether it's a positive number or a negative number, which you will know by looking at this most significant bit. Remember, the most significant bit will tell us, right, whether it is positive or negative. So depending on this most significant bit, I know whether the number was positive or negative. So if the number is positive, that means that the subtraction was successful. So which means my dividend, my quotient bit will be 1. So I will set this 1 bit in this last bit position over here. Okay. So that is, we are going to use this half of the dividend also to store the quotients one by one, because remember we will keep shifting it left. So as we shift left, there will be a empty position created here, which we will use to store the quotients. I will look at this last bit position, see whether that is 0 or 1. If it is 1, that means the number was, if it is 0, that means the number is positive. If the number is positive, then I can set the quotient bit to a 1 bit. If the number is 1, it means it was negative. So if it is negative, remember what I have to do? I have to do the restore operation. So I will add back the divisor here. So this control signal add subtract will tell me that I need to do an add operation. So I will add back the divisor here, get back the original dividend, and then do a shift left operation, and then do the subtraction again. Okay, these are the steps. Now again we will look at this with an example, so you will be able to clearly understand what is going to happen in this case. So this is our example that we will look at. Okay, so initially the value that I have here is 0 0 0 0 1 0 0 0. Okay, let me start with this. Now this is the division that I am going to do. The division I am going to do is 1 0 0 0 is my dividend, 1 1 is my divisor. Okay, just a simple 2-bit division is all we are looking at. So 4 bits are my divisors. Okay, so I have first, let's say first cycle I have 1 0 0 0 here, 0 0 0 0 is the value that I have in my A register. Okay, so what I do first, I subtract from this, I subtract the 0 0 0 1 1. Okay, I do a shift and then I do a subtract. What do I do when I do a shift and do a subtract? This is the shift that I am talking about here. 1 0 0, you will subtract 1 1 from that, right? So that is what we are doing. So if you do that subtraction, shift 1 0 0 and then do a subtraction, this is what I will get. What will I get? I get a negative number. So when I get a negative number, so accordingly I will have to set my Q0, the quotient bit based on that. So this bit is set, so when I do the shift, remember this position became empty. Okay, so when this position became empty, what do I do now? I set this Q0 based on this Q0, this is 1, which means negative. So negative, it means that I have to set the quotient bit as a 0. So quotient bit is set as 0, and then you will do a restore operation by adding back the divisor. So 1 1 is added back to this. So when I add 1 1 back to this, what will I get? I will get 0 0 0 0 1. Okay, when I add this is what I will get. Okay, and this quotient bit has been set. Next step is, again I will do a shift operation. Okay, we are doing one shift left operation over here. Okay, so that is what I am doing here. So I do a shift left operation. This is the shift left operation. So 0 0 0 1 that I had here has got shifted left to this position. So now I will do a subtract. When I do a subtract here, look at what I get. When I do a subtraction, I get this answer. So this number again, look at this. The Q0 again is this value is negative, indicating that the is 1, indicating it's a negative. So now again accordingly the next quotient bit is set to 0. Now because this value is negative, I have to do a restore operation. So add 1 1 back here. If you add 1 1 back, this is the answer you will get, 0 0 0 1 0. Now you will again perform a shift operation, shifted left here, 1 0 0 is become, and then do a subtraction. So when you do a subtraction, now you will get 0 0 0 0 1. So when I do a subtraction again, look at this, now the Q0 is 0, which means this subtraction was successful, right? That means you got a positive answer here. So this means that my quotient bit now will be set to a 1. So this bit is 0, this bit has to be 1. Now remember, look at this step here. After this, we are not doing any restore operation because the quotient bit is 1. Now you will only do a shift and then do a subtract. So do a shift, do a subtract. You get a value of 1 again. Again indicates that the quotient bit will be 0. And then because the quotient bit was 0, you have to do a restore operation. So the answer that you will have will be, add the 1 1 back here and you will get 0 0 0 1 0. This will become the remainder and the quotient will be 0 0 1 0. Okay, that is the answer that we got over here. In 4 steps, by doing shift and either subtract and add or just a shift and a subtract, you will be able to perform the division. Okay, so this is called as the restoring division method. Okay, so why is it restoring division as we saw? Just because every time we do a subtraction, and we find that the answer is negative, we will restore the value and then do the shift and subtract operation. Okay. This is just our simple normal division that we do, except that because we are getting our combination, whatever our circuitry to do the whole thing, we have to do this process of restoring back. Okay, that is what we have. So let us summarize what we have looked at in today's lecture. Are essentially two techniques. One is the fast multiplier, which is based on the carry save addition technique, and then we have looked at integer division, where we have looked at one technique called the restoring division technique. This restoring division, as we have seen, is very similar to the normal manual division that we do, except for an explicit restoration step that we have. Okay. And you can also see that the circuitry that we use for division is very similar to the circuitry which is used for multiplication, for sequential multiplication as well. So you can look at this therefore as a sequential division technique essentially, where you will have a shift right operation for multiplication, you have a shift left operation for division, which kind of makes sense, right? So that is what we have. Some questions for you to look at what we have studied today. Question number 1, what is the idea used in carry save multiplier? That is the fast multiplier. Question number 2, show the steps in multiplying 21 with 14 using the carry save technique, carry save multiplier. Question number 3, why do we do a shift left operation in restoring division? Question number 4, show the steps for the following restoring division 7 by 3. So if you try out these examples, you will be able to understand exactly how these techniques work. Thank you.